Okay, hello class. So today what I'm going to do is just go over the practice midterm that is in the file section on Canvas. Okay, so let me note this is this is longer than the midterm will be. Okay, I just wanted to add more problems so you have more things to review, but the midterm is probably going to be around 6 problems rather than 10. Okay, so I'm just going to go through the problems. I won't give complete explanations for everything, but this is certainly what you can ask me in the office hours. Okay, so let's just go through. So question 1, we had two sets A, which was the natural numbers where there exists some z and z, so that n is 2z plus 1, and B was the natural numbers where there exists k in z such that n is equal to 2k. And then we had to describe the following sets as simply as possible. Okay, so we have A intersect B, and I claim this is the empty set. Okay, so notice that A is precisely the set of even or odd natural numbers, and B is precisely the set of even natural numbers. They intersect trivially. Okay, so A union B I can write as just the natural numbers, because every natural number is even or odd. A minus B is just A, because the intersection is empty, and B minus A is just B. Again, but because the intersection is empty. So if I wanted to, explain some of these more, well, you could write, here you could write the equation 2z plus 1 is 2k, derive a contradiction from that. Here you can write any, n as 2z plus 1 or 2k, actually by induction. So you didn't need to provide full explanation. I'm just trying to give you a little hints as to how you do know these things. Okay, so that's question 1. Let me move it up. Oops. Okay, question 2. This asks, we assume that 3 statements are true. So we had that rainbows are colorful. 2, if something isn't sparkly, then it is extravagant, or then it must be extravagant. And finally, colorful things are never extravagant. Okay, and we were asked to conclude something about rainbows. Okay, so the first thing that you can conclude is that rainbows are colorful. Okay, that's by statement 1. But notice, of course, that we can say more, okay, because colorful things are never extravagant. So since colorful things are never extravagant, and rainbows are colorful, so we know rainbows are never extravagant. Okay, and now notice that, what we're saying is if something isn't sparkly, then it must be extravagant. Okay, the contrapositive of 2 is precisely if something is not extravagant, then it is sparkly. so I won't write that down. So, but this just implies, so since rainbows are never extravagant, the contrapositive here says that things that are not extravagant must be sparkly, so we can imply from this that rainbows are sparkly. Okay, so we have this, this, and this as facts that we can conclude about rainbows. Okay, question 3 was, well, my ordering got screwed up. I just left an empty item, so I'm just going to say question 3, check, since I forgot to add the question there. Okay, let me do question 4. So here this is A, B, and C are sets. So prove, disprove that A minus B union C is equal to A minus B intersect A minus C. So notice here, well, it says prove or disprove. So we should first figure out, whether we think it's true or not, and then see whether we can prove it. So to check whether you think it's true, it's useful here to draw the Venn diagrams. Now remember, if we wanted to disprove it, we would just have to find a single counterexample. To prove it, we have to use double containment. To check that, just to see which kind of way you should go, it's useful to draw the diagram and see if it works for this one. Okay. So let's see. So A minus B union C is precisely that set in the Venn diagram. Let me change color. So A minus B is going to be this set, and A minus C is going to be this set. Okay, so it looks from this picture that if I take the red and the yellow and I intersect it with the black, and I intersect them, I get precisely the black set. So I'm going to guess that this is true. Okay, and this isn't a proof, but now let's see if we can prove this. Okay, so we're going to do this by double containment. So I'm going to first show this direction. So let X in A minus B union C. So just by definition, this means, by definition, X is in A and X is not in B union C. Okay? So now what we have to show is that X is in A minus B and X is in A minus C. So this means, since X is not in the union, we have X is in A and X is not in B. So therefore X is in A minus B. And similarly, X is in A, and X is not in C, since it's not in the union. So therefore X is in A minus C, so therefore X is in A minus B, intersect A minus C. Okay, so that's one direction. Now we show the other one. So let X be in A minus B, intersect A minus C. So what do we know? Well, we know it's in both of these sets. So we know X is in A, and X is not in B, and X is in A, X is not in C. Okay? And we need to show that it's in this set. So we know X, so since we know X is in A, by assumption, or since it's in both A minus B and A minus C, it has to be in A. And then X is not in B union C because X is not in B and X is not in C, so we get X is in A minus B union C. Okay, so that's proved. All right, on to question 5, which was true, false, with a brief explanation. So I'll try to give a complete explanation here. So the first is the relation X is related to Y if and only if X is less than or equal to Y is an equivalence relation on N. Okay, so notice this is going to be false. And the reason is, well, so it is a relation, but we have to check whether it's reflexive, symmetric, transitive. So it is reflexive, so I'll give kind of more explanation than you would be required to do. It is reflexive because if X is less than or equal to, because X is less than or equal to X, in particular, X equals X. I'll do transitive as well. So it is transitive, right? Because if X is less than or equal to Y, and Y is less than or equal to Z, this implies X is less than or equal to Z, but on the other hand, it's not symmetric because, and now I'll just come up with an example. 1 is less than or equal to 2, but 2 is not less than or equal to 1. Okay, so it has to satisfy, if it was an equivalence relation, it would satisfy those 3 properties. Since it doesn't, it's false. So the second one was the 2 people are related if and only if born in the same month is an equivalence relation on the set of people. Okay, and this turns out to be true, and to see it's true, we'll just go through the 3 properties. Well, person 1 is related to themselves? Yes, right? Because you're born in the same month as yourself. Symmetric, P is born in the same month as person Q. If Q is born in the same month as person P, yes. And finally, if P is born in the same month as person Q, Q is born in the same month of person R, then they're all born in the same month. So we get that P is born in the same month as R, so it is transitive. Okay, that's question 5. Okay, so for question 6, we had a function, and we need to again prove or disprove statements. So we had let f going from A to B be a function between sets A and B. And we have a subset, and C is a subset of A. So I want to prove or disprove the following statements. Okay, so the first one is f of A minus f of C is contained in f of A minus C. And the second, which I'll just put down here, is that f of A minus C is contained in f of A minus f of C. Okay, so notice if both of these statements were true, then, then these two sets would be equal, okay? Okay, so let me draw a picture first, just down here, for what we're kind of expecting to see. So we have our set A. Inside is our set C. We have a set B and a function. So f might not be injective or surjective, but so f of A is sitting here, and then inside it is f of C. So now let me draw the other sets that we're interested in here. So here is, in yellow, we have A minus C. Over here, okay, I'll make it red. We have f of A minus f of C. And so notice what the question is asking is whether this A minus C, which I'll draw in blue now, whether this A minus C is sent into f of A minus f of C. Okay, and then whether this is honestly equal. Okay? So I claim that this is going to be true for one of them and false for the other. Okay, so let me try to tell you what can happen. Okay, so the problem here is that I might take an element x, which is in A minus C, and f sends it into f of C. Okay, so I can have x in A minus C, where f of x is in f of C, and hence not in f of A minus f of C. Okay, so I'm claiming that this second statement is false. And now you can see kind of how to construct an example. I'm going to move back to black. I don't know why I'm stuck with blue. So let's just take A to be this 1, 2, the two element set. B is going to be also the one element, the two element set 1, 2. And C is going to be the set containing 2. And my function just sends both things to 2. Then f of A minus f of C is empty. But of course, f of A minus C is not empty. It's the set, the image of that set is the set containing 2. Okay? On the other hand, from the picture you can see, so f of A minus f of C is the red part. And it should be contained in the image of the yellow, right? So the problem, let me just try to go back to this picture. The problem was that the yellow could intersect f of C. But I claim it should contain it should cover this red region, because the things in this set, in the red region, are in the image of some element, and we know that they're not in the image of an element of C. Okay? So now I'm claiming that this picture should, let me go to black, should tell us that this should be something that we can prove, and let's try to do it. Okay? And the way to do it is just do it a containment proof. So let x be in f of A minus f of C. So what does this mean that we can say about x? So we know, well, x is equal to some f of A for some A in A. And we know x is not equal to f of C for C and C. Okay? So therefore, A has to be in A minus C, because otherwise x would be in this set, and therefore x is in f of A minus C. Okay, let me go now to question 7. Pull this up. Okay, so this one says construct a function from n to n, which is injective but not surjective. So injective, not surjective, and then surjective, not injective. Okay, so how do we do the first part? Well, again, you just have to come up with 2 explicit examples. So injective, not surjective, can be f of n is equal to 2n. Okay? So it's not surjective because 1 is not in the image. And it's injective because 2n1 equaling 2n2 implies n1 is equal to n2. Okay, so if I have 2 natural numbers that get sent to the same thing, they had to be the same. Okay, surjective, not injective. I'll just do a piecewise function to say that, to make it simple. So I'm going to say f of n is equal to 1 if n equals 1, and n minus 1 if n is greater than or equal to 1. Okay, so I'll just draw the picture here. You can just imagine what this does. It sends 1 to itself and then just shifts everything else by 1. Okay, so it's not injective because f of 1 is equal to f of 2. So again, this is something where you kind of have to check. If you want to show a piecewise function is injective, you have to check both parts separately, and then you also have to see that they don't intersect. So, oh, sorry, I think I said n greater than or equal to 1, but of course I meant n greater than or equal to 2. Okay, so 2 goes to 1. And then what's going to happen is that these domains are going to the range will overlap, so 1 and 2 get sent to the same thing. And it's surjective because either you have a natural number which is n plus 1 for some natural number, or it's 1. Okay, and 1 gets sent to 1. All right, question 8. Okay, so I'm going to do a different one actually, because question 8 is the same as a lecture problem, and the solution should be in the lecture problem solutions files. Okay, so sorry, that was just a mistake on my part. But let me do a different one. I mean, luckily they're all kind of in the same in this case, so the same, you just have to kind of do a different algebraic manipulation at the end. So I'm going to show you the sum from k equals 1 to n of k squared is n times n plus 1 times 2n plus 1 over 6. Okay? Okay, so what do? We first check the base case, p of 1. Well, in this case we get 1 is equal to 1 times 2 times 3 over 6. So we are happy. Okay, and now there's too many letters here, so I'm just going to prove that p of j implies p of j plus 1, since k is busy. So I'm going to prove that from k equals 1 to j plus 1, of k squared we have to show is equal to this formula. Okay, so this is equal to 1 squared plus 2 squared up to j squared up to j plus 1 squared. And this is equal by induction, so by p of j, we know that this is equal to j times j plus 1 times 2j plus 1 over 6 plus j plus 1 squared. Okay? And now we want to rewrite this as a fraction, or as a single fraction, to get this formula with j plus 1 in there for 1. Okay, so let's see what we get. So this is equal to j times j plus 1 times 2j plus 1 over 6 plus 6 times j plus 1 squared over 6. So this is equal to j plus 1 times j times 2j plus 1. Oh, sorry, so let me, plus 6 j plus 1. I think that's right. Okay, so I pulled out a j plus 1 from both sides and then combine the fractions. So this is equal to j plus 1 times, let's see, 2j squared plus j plus 6j plus 6 all over 6. So this is j plus 1 times 2j squared plus 7j plus 6 all over 6. And if life is fair, this should be equal to 2j. I'm just going to go, you can see me figuring this out in real time. 2j squared, then I have a 3 and a 2, so I guess I should have a 3 here, a 2 here. That looks right. Over 6. And this 2, so this is j plus 1, so then this is j plus 1 times j plus 1 plus 1 times 2 times j plus 1 plus 1 all over 6. And now going all the way up to the very top, woo! You see this is exactly what you get when you plug in j plus 1 into this equation. Okay, so that's induction proof. Okay, so we had 2 more problems. So the first one was question 9. Does there exist a bijection from n to z? If you believe the answer is yes, give an explicit function and prove that it is a bijection. If you believe the answer is no, prove that no such bijection exists. So this comes from the homework problem that you did in class, or did on your second assignment. Okay, so the answer is yes. And for an explicit bijection, you can construct f of n equals n minus 1 over 2 if n is odd, and minus n over 2 if n is even. Okay? So to check that it's injective, well, again, you can check this for each function, on each function. Where it's pretty easy to work out that this has to be injective here. And note that the ranges, or note that the images, are disjoint. because f of the odds are all greater than or equal to 0, and f of the evens are all strictly less than 0. Okay, so for surjective, well, we have two cases. Well, so first we have maybe 0 is a case. So 0 is f of 1. Then we could have n greater than 0. This is in the image of f of 2n plus 1. And n less than 0 is in the image of f of 2n. Okay? All right, and then question 10. We had a true-false with, again, a brief explanation. There is a bijection between R and R minus the natural numbers. Okay? All right, so how do we, the answer turns out to be true. You can think of this as, well, you're taking an uncountable set and you're removing a countable set. Well, we do know that this must be uncountable. Right, because the real numbers are equal to the reals minus the naturals union the naturals. Okay, so since this is countable, if this was countable, then the reals would be countable, but we know they're not. Okay, so we know they're uncountable, but why do they have to have the same cardinality of R? So here's the idea. Remember, at this point, to construct bijections, kind of our best tool is the Schroeder-Bernstein argument. So we just have to construct injections from R to R minus n and R minus n to R. Okay, so it's usually just much easier to construct injections than bijections. Okay, in particular, this one is completely trivial. This is the inclusion map. Okay? This one is trickier. But remember, we showed before that we could make a bijection between R and 0, 1. And the graph of the function looked something like that. Okay? And therefore, since, notice that the image is in 0, 1, so I guess technically I've drawn you the picture which goes from 0, 1 to R. Okay, I'll draw you the other one. It just is the inverse of this function. Looks something like that. So there's a function that goes from R to 0, 1. So since the image is in 1, the image is in R minus the natural numbers, since there's no natural numbers between 0, 1. Okay, so therefore we've constructed an injection from both sides, so Cantor-Bernstein tells us that there must be a bijection between them. Okay, so that was the midterm. So more questions in office hours, please. All right, have a good one.